In this lecture, we're going to discuss how you can lift paths into the covering space. Now, I should say that maybe this is like a warning that our theorems are not the most general. So we're making some assumptions. We assume that things are path connected. We assume our spaces are locally path connected. We assume our spaces are Hausdorff. So these are generally the three assumptions we make about our topological spaces. And we also assume that we're working with covering maps. A lot of these assumptions can be dropped. Sometimes you can drop all of them. Sometimes you can drop some of them. To add even more confusion, I think this is done in Breton. He actually drops the path connectedness, and he talks about something called being locally connected. So that makes it even more confusing. And then we also talked about the difference between a covering and a local homeomorphism. So if you want to make this even more confusing, you can sometimes restate certain theorems using local homeomorphisms instead of coverings, but I'd rather not go there. We're not trying to be as general as we could be. We're just doing what is relevant for us. So we'll just continue to assume our usual three assumptions, and we'll assume our maps are covering spaces. So this is just like a warning about generality. If you open up different sources, different books, you might see some of the theorems presented in a different way, and that's only because they're trying to be a little bit more general. So let's start with, this is called the lifting property of covering spaces. So here's how it goes. So let pi from x to y be a covering map, and you're going to pick something in y. Kind of think of it as like an initial condition. And let's say any x0 in the fiber over y0. So in other words, it's a point that maps to y0. So maybe to simplify notation, you can write that you've chosen this base point and you've chosen this base point. So all you're saying is this is a covering map, and you're picking this point to be the one that maps to y0. Now, the reason why we're picking initial conditions is because, as you will see in this discussion, we will have certain choices that we have to make. And the initial conditions will sort of specify the choice that one has to do so that it's clear how the rest of the argument goes. So like basically, in order to get uniqueness, you will have to have certain choices. And that's where the initial conditions come into play here. So let's say what the property is. So say that f is a path in y, is a path in y, and let's say f of 0 is equal to y0, and f of 1 is equal to y1. So it's a path. We do not assume it's a closed path. They could be two different points. And there exists, so this is the property, there exists a unique path. And the notation that people use is they just put a tilde on it. So f tilde from 0, 1 into the covering space with f tilde of 0, so the initial point goes to x0. So this is the point in the fiber. Now you should notice, and you're probably thinking this right now, you'll probably notice, well, what about this one? So this one actually plays no role whatsoever. So you can delete this, okay? So this plays no role. Just think about initial conditions, okay? So you're basically saying, so to put it in very simple, I did not say what the property is. So there exists a path with the property that pi composed f tilde is f. Okay, so the picture that people like to draw is, this is y, this is a path, f, this is your covering space with pi, and you're saying that it's a path in y, but the path can be lifted up, can be sort of enlarged. I'm not sure if enlarged is the right word, but it can be lifted into the covering space. So you can come up with an arrow over here, f tilde, that will make this diagram commute. Okay, so that is called the path lifting property. And what you're doing is you're looking at initial conditions. So you're saying that at time 0, that's the initial condition, this path f, it starts at x0. And now you have to make a choice. There is infinitely, well, let me take it back. There could be an infinite number of points in the fiber. So you pick any one of those. This should have been, sorry about that, that should have been y0. There could be an infinite number of points in the fiber, and you just pick one of them, right? You're making a choice. That's an initial condition. This is your x0. So you're making a choice. So you're saying that if I give you a path that begins at a certain point, that point, it lifts into x. It might have infinitely many choices, but you pick one of them. And once you pick one of them, then the rest of the path is determined. So maybe a picture will help here. So remember how we think of a covering map. We sort of think of a covering map as, like, going back to our example, this is sort of our stack of pancakes example. So this disk over here represents y, and above it you have this sort of stack of pancakes. This entire thing represents x, and you have a projection. You're sort of just dropping all of these back to y. Now what you're saying is very simple. You're saying that if you have a path, so let's say you have a path over here that starts at y0, you have some kind of path, and you pick, like, the fiber of that point. There's, in this picture, there's 4 fibers, so you're basically choosing a pancake to use. So once you choose a pancake, that means you basically specify x0. The rest of the path can now be lifted, and it stays in that pancake. And then it, as you can see, it projects back down to the path that you have. Now, this is not the best example, because sometimes, sometimes what would happen is, sometimes you start in one pancake and you end up in a different pancake. I know this picture is not really the best picture because our space is not path connected. You see, our spaces are usually path connected. So that's why we have a little bit of an issue here. But this is just for illustrative purposes. So that's the property. Now, how do we prove it? So we first begin with a simplifying assumption. And this is sort of like the main idea. So how do you prove this? Proof. So I noticed that a lot of books, when they prove this, they often jump immediately into the most general type of argument, and then it looks a lot harder than it actually is. But I think if you do it in the simple case first, it makes everything a lot easier. So first assume, and this is for simplicity, that the image, so this is the image of this path, is evenly covered. In other words, we can find a U. So we can find an open set in Y. So Y is the base of the cover. X is the covering space. Y is the base of the cover. So that the path, so this is the image. You have to be a little bit careful. It would be very suspicious to write U is a subset. I'm sorry, F is a subset of U. This does not make sense. F is technically a mapping. What we're talking about is we're talking about the image of the mapping. We're basically talking about this red curve over here. So this is the image of the mapping. So the image of the mapping is completely contained in U, and U is an evenly covered open set. Okay, so So in fact, we're sort of getting a picture like this again. So then what would that mean? That would just mean that if this is, so this is you, this is your path, the path begins at the point y0, and because it's a covering space, you have this stack of pancakes. So this is pi inverse of u. Okay, so u is evenly covered, so thus pi inverse of u is a union of vi, and every vi, these are the path components, they're open sets. So these are the path components, so it's a union of all of these. And we pick an x0. Okay, so you're going to pick vi with x0 in vi, because this x0 is in the fiber. X0 is one of the points that gets mapped to y0. So it's somewhere. Let's say it's over here, x0. So it's therefore in one of these. Let's say it's in vi. And now here's the idea. I'm going to redraw this picture for you again. So what are we trying to do? So I'll draw it over here in the corner. We have the following diagram. We have x, we have y, we have 0, 1, and here we have f. And we're trying to construct, this is pi, and we're trying to construct this f tilde. So the property that we want is we want f to be equal to pi composed with f tilde, right? This is what we want. Now, supposing that you can move the pi over to the other side, you would get that pi inverse composed with f is equal to f tilde. And that's how you construct the f tilde. Now, the problem with this kind of argument is that pi is not a homeomorphism. It does not necessarily, I mean, the inverse might not exist. So you're sort of cheating when you're doing that. But this kind of cheating proof is actually the idea of how this works. Because once, you see, you're assuming that the path completely sits in an evenly covered neighborhood. And this is the point in the fiber. So when you take this blue curve, well, you can pull it back. It will be contained in here somewhere. So you have some kind of curve, you have some kind of blue curve. Well, you actually do not even care about that so much. But what the main point here is you have a mapping. This is vi. And pi, when you restrict it to vi, is a homeomorphism. And now suddenly you can do that. Okay, so you're going to pick a vi so that this is satisfied. And we know that when you take the covering map and you restrict it to this smaller open subset, then you have a homeomorphism to u. Okay, so, and then how do you end up defining this f? And now you can set f tilde to be equal to, and that's exactly what we just did, except now you can do it because on this, between these two open sets, this is a homeomorphism. So you can get away with this kind of argument. So then you would just say it's pi, you would just take pi, restrict it to vi, you take the inverse, and you compose it with f. And then f tilde would be a mapping from 0, 1 into, so if you carefully think about this, f maps you from 0, 1 into y. It maps you into y, but really it's contained in u. So you could replace y by u. And x maps you into here, but you can replace x by vi. And then this pi is just the restriction, and this is a homeomorphism. So now you've constructed the required map, f tilde. It goes into vi, but vi sits inside, right? You could write vi, but it sits inside the covering space. So it goes into x. And you can check that the initial point of that path is equal to the initial condition that you gave yourself, that it's equal to x0. and then the proof is complete. So that's how you do it. But how would you make the argument more general? So this is really the main idea of why you can do this. This is exactly how you're using the covering property. Now, to generalize this further, here's what you need to do. Okay, so, and it's a trick we've seen before. So to generalize this argument, and I think this will probably make a good homework problem, what you basically do is, in general, when you have a mapping into Y, the image, so this is the curve that you get in Y, it will usually not be contained in a single evenly covered open set. But what you could do is you can contain that piece of it, you can contain that. You basically do it on pieces. You can cover it by a finite amount of evenly covered open sets. So so the terminology is kind of funny. You're covering a set by a finite amount of sets that themselves are evenly covered. I mean, there's like two different meanings of cover here, but that's just a funny terminology, the way it works out. But you're kind of using compactness here. You're using the fact that this is compact. And the basic idea here is you're just going to partition 0, 1 into pieces. So think of this one as time 0, think of this as time n, and then you just partition it into equally spaced pieces, let's say. You just break up the interval into equally spaced pieces, n of them, so subintervals, where each of these subintervals end up in one of these. So you have a piece over here, then you have a piece over here, and you kind of piece them together to get a path all the way in the covering space, okay? And that's essentially how the argument goes. And the choices are unique. There's only one way to do it. Because in the previous, if you go back to the previous argument, that map was forced on you. It had to be given by that formula, because when you try to solve, right, so when you go back here again, this is 0, 1 into Y, this. Like, this F tilde is forced on you. The way you get it, I mean, everything's completely forced. The way you get F tilde is, it would be, well, the arrow goes the other way. So the way you get the F tilde, it would be F composed pi inverse. That's what it has to be. The only problem is pi inverse does not necessarily exist. But assuming the path ends up in an evenly covered neighborhood, you can do that. You can do that on that path component, and it's the same kind of argument that when you have that, like, let's say we just look at these two intervals. This is a piece of a curve. So you have like a piece of a curve from one point to another point, and then after that you have another piece of the curve, and you can lift this curve. So this point over here, this is the y0 point, it lifts to x0 in the covering space. And then this terminal point, so this terminal point has to match with the initial point of this curve. And so since you've specified how the curve begins, you're then forced to lift that however it lifts. And so the choices are all completely forced on you. So it's a homework problem to try to figure out how to generalize that without the assumption that the curve is evenly covered itself. But it's not too difficult now that you see the general idea. So now I want to show you an interesting way this can be used. So this lifting property can be used to rigorously define what we call the winding number. There are different ways to do it. In the previous topology course, if you took it last semester, we did it a little bit differently by using angles. And one can argue that these approaches are in some sense equivalent. It's just that the notation is a bit different. But regardless, let's see how one can define the winding number. We're not really going to use the winding number that much this semester, but it's just nice to see how you can use this machinery of covering spaces to define this winding number, which is actually useful in, let's say, complex analysis. So let's assume, so what's the idea here? So the idea here is let f be a closed curve, a closed loop, let's say in the punctured plane. So missing the origin. So f of 0 is equal to f of 1. So this is a closed path, or you can also call this a loop. And let's assume, so we have to make some kind of initial condition. So let's assume, for simplicity, it does not really matter, but let's just assume for simplicity that f of 0 and f of 1, they both begin at the point 1 plus 0i. That's the simplest point to use. So the idea here is this is our punctured plane, so it's missing the origin, and then you have a path that begins and ends. It might do something really complicated, and then returns back to the origin. And it never goes through the origin, and then the question becomes that when you draw the origin over here, so that's the origin, there's this question of how many times does f wind around the origin. So we're just using the origin for convenience. You can really do this around any point that's not on your curve, but then you sort of translate things over. Like in a complex analysis course, they would probably talk about winding numbers in general around an arbitrary point, but it's the same idea. You can always translate things back to the origin. So how many times does the path wind around the origin? So you sort of, it's like a counting problem. How many times do you go around? That's what it means intuitively. But how does one actually define it? So this is the interesting approach here. So as I said, this is not something we're really going to use much in this course. In the previous topology course, we used this a lot more. But I just want to show you maybe a nice example of how you're lifting paths. And this is a nice thing to know in general. So here's how you do it. So we're going to use the exponential map. So this is the map exp. So the exponential map from the complex plane to the punctured plane. So this is just exp of a complex number is e raised to the complex number. If you want, maybe you can even make it like e to the 2 pi z. Does not really matter. Let's just keep it like this. So we're going to use the exponential map, and let's choose. So we need to pick something in the fiber. So the point that we've decided to begin everything at was 1. So we need to pick something in the fiber. So let's say, so let's actually do it like this. Let's have this be a covering map. We have to pick something in the fiber that goes to 1. So for simplicity, as we've said, we're just using 1. And the easiest number that maps to 1 is 0, right? E to the 0 is 1. So this is what we've decided to use for our initial conditions. So now, given a loop, so this is a closed path f from 0, 1 into the punctured plane with f of 0 is equal to 1. Maybe it looks nicer if you write 1 plus 0i. So you're sort of indicating what its real coordinates are, so you kind of see it a little bit better. There's a unique lift f tilde from 0, 1 into the covering space. Now the covering space here is the entire complex plane with exp of f tilde is equal to f. Or if you prefer, if this makes you feel better, you can say that e raised to the f tilde will give you f. That's basically what you're saying. So there's a unique lift. And with the initial condition, I forgot to say this, with the initial condition that f tilde of 0 is equal to, so which point did we decide to use? We decided to use 0. Now, this is the part you have to be careful about. So Now, just because f of 1, that's the terminal point. That's the terminal point of the map f. The terminal point also finishes at the same complex number. Does not mean that f tilde of 1 is equal to 1. So why not? Well, because all we know is that f is equal to exp of f tilde with the initial condition that f of 0 is 1 and f tilde of 0 is 0. That's all we know. But if we were to look at, let's say we were to evaluate everything at 1, we would have that f of 1 is equal to the exponential of f tilde of 1, which will imply, now we know that f of 1, because it's a closed loop, this is equal to 1 again. So that's equal to the exponential of f tilde of 1. And so it means that, maybe this notation will make it easier, that e to whatever that is, you have a power, is equal to 1. And complex exponential is equal to 1 is precisely when it's a multiple of 2 pi I n. So that's when you're going to have it equal to 1. And so the consequence from here is that we get that f tilde of 1 is equal to 2 pi I n, and not necessarily that it's equal to 0. It could be equal to 0, it could be equal to n, but it's a multiple of 2 pi I. And this is the number n that we call the winding number. So here's the way the winding number is defined. So to summarize, to find the winding number of f, we lift f to f tilde. So in other words, it just means we write it in the form that f is the exponential of something with the initial condition that f tilde of 0 is 0. And then we compute the winding number. And then maybe I should say it like this. And then from here it will follow. And then f tilde of 1 would be a multiple of 2 pi I. And this multiple, whatever multiple that is what we call the winding number. So this is how you can end up defining the winding number. It will, in the end, tell you how many times you wind around. Now, if you're confused by this, like for instance, you might ask the following question. You might say, we have a closed path, let's say, that begins and ends in the same point, x0. I'm sorry, it begins in the same point, we call it 1. So when you're lifting it, initially you lift it to 0. And how can it be that it goes to maybe a different point, right? That's basically what we're saying. This is the path in the punctured plane, this is the path in the base space, and this is the path in the covering space. And as you can see, the path in the covering space, it's not necessarily a closed path anymore. So how can this possibly happen? Well, basically what's happening is, when we're doing the lifting property of paths, we're basically breaking up the path into pieces over which you have an evenly covered neighborhood. That's kind of the idea. You're kind of partitioning your path into pieces, and then you're using the covering. You can then use pi inverse, right? You can take the inverse of the covering map, because locally it has an inverse, and you kind of pull them back to the covering map. But you have to understand that this piece, this blue piece, might sit in one pancake. This sits in a different pancake. That one sits in a different pancake. So they can all be sitting in different pancakes. So when you complete the journey, you might end up in a different pancake. And that's the reason why the terminal point does not have to match the initial point. That's really what's going on here. Maybe just to illustrate a very simple example, here's a very simple example. So we can have a function. This is our path into the punctured plane. And it has the property that f of 0 is e. So actually, let me give you the formula for this. So f of t is e to the 2 pi I t. And f of 0 is equal to 1, and f of 1 is equal to 1. So it's a closed path. But when you lift it into the covering space, so that's the entire complex plane, f tilde would then be the path. So it's the part of the exponent. It's just the path 2 pi I t. And you notice that f tilde of 0 is equal to 0. So then we have the relationship that the original path is the exponential of the lifted path, right? Because the lifted path, it's the one that appears in the exponent. But the endpoint of the lifted path is now equal to 2 pi I times 1. And so 1 is therefore going to be the winding number, because it's one multiple of 2 pi I. And this makes sense, because this is the path, when you draw it, this is the path that goes in a perfect circle exactly one time around. So that's why the winding number is 1. So this just illustrates that the endpoint does not have to end up where the initial point is in the covering space. So now let's get to homotopy. So the next thing we'll talk about is lifting not just paths, but path homotopies. So here's how this goes. So as before, we assume that pi is a covering map. And let's say this is the initial condition, is a covering map. But you do have to specify the initial condition to get uniqueness out of this, because basically the initial condition tells you which of the pancakes you begin with. Once you begin the journey in a pancake, from that point on, everything is determined. Okay, so this is a covering map, and we've specified some initial conditions. And say that f and g are two paths. So these are paths in the base space, because we're going to be lifting them. These are paths in the base space with let's say they begin, yeah, so with f of 0 is equal to g of 0 is equal to y0. And let's say f of 1 is equal to g of 1 is equal to y1. So they both finish at the same point. This point that they finish does not have to be where you begin. And let's also assume and suppose further that f and g are path homotopic in y. So what does that mean? That means there's a path homotopy map. There's this map H, 0, 1 cross 0, 1 into y with, so the way I always like to do it is the first one I like to think of it as time, and the second one I like to think of it as interpolation. Some people do it the other way around, but this is the way I like to do it, with h of t comma 0 with, let's write it like this. So when you set s is equal to 0, this gives you the first path. When you set s is equal to 1, it gives you the second path. When you set, now if you set t is equal to 0, then the path homotopy, it stays, well, the picture is this, that you have y0, y1, and this is f, and this is g, and this is just a homotopy. That's what this is supposed to represent. The points never move. The end points and the beginning points, they never move. So for all time, this interpolation never moves this point, and the same thing with the other one. And this is going to be h of 1 comma s is y1. So this is a path homotopy. And what's interesting is you can lift a path homotopy also. Now, before I write down the result, I want to draw a picture first. So this path homotopy, it's sitting inside Y. This is the base space. And up here, we have the covering space X. And this is our covering map pi. Now, if you take this lower, so you specify the initial condition. So you're specifying x0. You specify the initial condition. And this lower edge, this is a path. So this path can be lifted. So you're going to get some G0 out of you're going to get G tilde out of this. And this path can be lifted. And you're going to get another F tilde out of that. But because the initial condition is on the initial points, you might say that there's no guarantee that they end at the same point. So maybe it looks something like this. Right? That's what you would feel. I mean, based on the previous example, that the initial condition is only at how the paths begin. And so this is really the kind of picture that you're going to end up getting. But this is the part that's going to be, at first, a little bit surprising, but then we'll explain it. So then the proposition here is the path homotopy map H can be lifted into a path homotopy map, into a path homotopy. H tilde from 0, 1, cross 0, 1 into the covering space, so that H tilde of T0 would be the unique lifted, so F tilde of T, that's the unique lifted path for F. H tilde T1 would be the unique lifting of G. And then the other conditions get satisfied, that H tilde of 0 S is going to be X0 for all S. And H tilde of 1S would be something X1, where X1 is something in the fiber. So it's something in the fiber of Y1. So in particular, they do in fact end in the same point. So the lifted path F, its terminal point, and the lifted path for the other path, its terminal point, they're actually the same, which is, at first, it feels a little bit surprising, but this is what the proposition says. It says that path homotopies can also be lifted. So you can lift paths, and you can lift path homotopies as well. So what's the explanation for this? So the explanation for why this works is nicely explained through a picture. So this is a square. So we are mapping a square, I cross I, into X. I'm sorry, we're mapping this into Y. Now the lower piece of the square, so that's the lower part of the square. So this is what happens. So this is the lower part of the square. The lower part of the square gives you the some kind of path F. So this is going to give you some kind of path. This is F. It starts at somewhere, let's say Y0, and it finishes somewhere, let's say at Y1. The upper part of the square, because it's a homotopy, this is the upper part of the square. When S is equal to 1, you get the other path G that also begins and ends at the same points. This is G. This is the other piece of it. Now, the left edge, so when you keep t is equal to, so if you set t is equal to 0, and you let s vary from 0 to 1, you are getting another path. This is a path, right? The time parameter does not move, but the interpolation parameter moves from 0 to 1. So this itself is a path. So you are getting a path that stays constant. You have a constant path that stays at y0. So that's a constant path. So this entire left edge that you have over here, this entire left edge, this is actually a constant path that stays constant at y0. And this entire right edge is a constant path that stays constant at y1. Now, think about what you're doing. You're trying, so you have a homotopy. This is your homotopy map H. And up here, X, that's your covering space. And you're trying to lift it. So you're trying to lift it to, you're claiming that you can lift it to H tilde. And this is pi. So it has to do with the fact that you have 4 separate paths, and they can all be lifted uniquely when you specify where the path begins. So this lower edge in the covering space, right? So when you lift it to the covering space, I mean, I guess I'm out of room over here, so I'm unfortunately I have to take this down. But when you lift this lower edge to the covering space, so y0, it goes somewhere. It's the one we gave at the beginning. That's the initial condition. So that's the x0. That's the initial condition. And this is the lifting of f. This is f tilde. That's the lifting of f. Then we have a lifting of g. So g lifts, and it starts at the same point because that's the initial condition. So there's unique liftings for f and g. Now here's what you need to realize. This left edge, this entire left edge, it is a constant. Okay, this is a constant path in y. So you could at first think that maybe this left edge, when you lift the left edge, maybe it returns back to itself. Maybe that's the way that it lifts. It kind of goes back like this. But that cannot happen because this left edge is the constant path. So when you lift it, it can only lift to the constant path because of uniqueness. So this entire left edge, it has to stay constant and be that point. And for the exact same reason, this entire right edge, at first you might think that maybe this entire right edge, when you lift it to the covering space, maybe it does something like that, right? It's a path between 2 points. So between 2 points in the covering space. So you're getting some kind of path. But then you realize that this entire path, when you project it, it goes down to a constant path. Okay, and so the path that does that for you is the constant path itself. It's just a constant lifting. Because of uniqueness, it has to be the constant path. So this means they cannot be separated from each other. They have to come together. They have to come together. And so they have to come together, and it has to stay constant. So basically what you've just shown is that the path homotopy lifts in a unique way also. It exists and it lifts in a unique way. So let's maybe summarize all of that into a proposition. So here's a proposition. This is it basically says that path homotopies lift. And in fact, they lift uniquely once you specify initial conditions. So here's how it goes. So you're going to assume that you have a covering with initial conditions is a covering, and f and g are 2 paths in y, in the base space, with f of 0 is equal to g of 0 is equal to x0, and f of 1 is equal to g of 1 is equal to x1. So 2 points. So these are 2 paths in the covering space. And let f tilde, g tilde, from 0, 1 into x be the unique liftings with f tilde of 1, I'm sorry, with f tilde of 0 is equal to x0. Oh, I made a mistake. I meant to say these should have been y0, y1, and this is g tilde of 0 is equal to x0, be the unique liftings. So this is the previous proposition, be the unique liftings. So if F tilde and G tilde, let me take it back. If the original paths of F and G are path homotopic in the base space, then F tilde and Y tilde satisfy the condition that their terminal points are actually equal, and furthermore, that they're homotopic to each other. They are F tilde and G tilde are path homotopic in the covering space. I mean, I guess you could say that this piece over here, you can say, is a little bit redundant. It's not really necessary to say that, because if they did not have the same endpoints, then it would not make sense to say that their liftings are path homotopic, right? I mean, the moment you're saying they're path homotopic sort of implies that. But in particular, what that means is they have to finish at the same endpoints. So the way you prove it, it's almost the same proof. So I'm just going to, so this is a sloppy proof in order to save time, sloppy proof. This is essentially the same proof as before. So basically, you first assume that, so okay, so it's about lifting the homotopy. So so this is the way you start. You say let H from I to I into X into Y be a path homotopy between F and G. And then you're going to assume at first that the image of the square is evenly covered. Okay, and then we can lift H to H tilde by doing the same thing as we did before. So you would do H composed pi inverse. I mean, that's basically what you can do. It's the exact same proof. And then if it's not evenly covered, you take the square and you break it up into pieces so that every subsquare is evenly covered. So it's the exact same proof. I mean, it's not super exciting. You can find books that write it out for you, but you should be able to do it yourself. It's not exactly the most exciting thing. But what I want to get to is like the important idea of this. I mean, of course, it's important to verify all of this, because otherwise the math does not work out. But math is about the big ideas. And sometimes working through these technical proofs, you run out of time to talk about the big idea. So this is like the big idea that I wanted to get to, that there's a nice theorem in algebraic topology, and it's called the monodromy theorem. Monodromy theorem. And here's how it goes. So suppose we have a covering. Suppose this is a covering. And X is simply connected. So the covering space is simply connected. What does that mean? I.e., this is going to look funny because we have two different pi's. Pi 1 of X comma X0 is trivial. It's the trivial group. Okay, so this pi is the covering map, and this pi 1, that's the fundamental group. So simply connected means it has a trivial fundamental group. Simply connected also means it's path connected, but we're already assuming our spaces are path, so we're not going to bother to write that out. So X is simply connected. It has a trivial fundamental group. What does this mean? To quickly remind you what this means. So trivial fundamental group, it means that means that every loop at x0 can be shrunk down to a point. Down to a point, not a path. And shrunk down to a point, this is just another way of saying it's path homotopic to the constant path. So all loops shrink down to the constant path, homotope down to a constant path. That's what it means to be simply connected. Okay, so here's the monodromy theorem. So the monodromy theorem says that let F and G be loops at y0 in the base space, y. So it says that F is path homotopic. I'll write it like this. I know this is the overused symbol in topology and all of math, but they're equivalent as a path homotopy. So F and G are path homotopic if and only if when you lift F and when you lift G and you look at their final points, they're actually equal. They're the same point in the covering space. Maybe I should have, for the sake of completeness, I should have said what F tilde and G tilde are. And maybe you pick and then you're going to let F tilde and G tilde be the unique liftings of F and G with the fiber that they both are beginning at x0, right? So you have to specify that initial condition, and then you can lift uniquely. So if they happen to be path homotopic, then they have the same terminal point. And if they have the same terminal point, then they happen to be path homotopic. So how does one prove this? Well, we just proved one direction. Actually, this is why it's called the monodromy theorem. So monodromy, if you translate that word into English, it's sort of like the theorem of the single value in a way. That the mono, it's a theorem of a single value. That the equivalence between two paths as homotopies is completely determined by a single value, and that's the way their endpoint lifts in the covering space. That's why it's called the monodromy theorem. So how do we prove this? Well, we just proved one direction. So this one we just proved. That's the homotopy lifting property, because if these are path homotopic, then you can take that homotopy itself and lift it into the covering space. And if it's a homotopy between their liftings, then in particular, the liftings must end at the same point. And so their terminal points are the same. How do you go in the other direction? So the other direction is fortunately very simple if you approach it the right way. There's just a trick you need to know, and then it works out correctly. So proof. So we will justify the direction that goes like this. So recall, and this was on the homework, so you have to recall this fact. This will make it a lot easier, that since pi 1 x at x0 is, or maybe I should just say it like this. So since x, I think this would be better. So since x is simply connected, any two paths that begin and end at the same point are path homotopic. And so that was the problem that you had on the homework, that if you have two paths, here you're not assuming that these paths are close paths. These are just any two paths between any 2 points. If they both begin and end at the same point, then those two paths are homotopic. And the quick version of this is, just to quickly go over it, I'm not going to go over that homework problem, but basically, if you have one path going like this, and you have another path going like that, if you take the reverse path going, if you just take the reverse path like this, then you've just created a closed loop. And then that closed loop can be deformed down to a point. And then you just sort of manipulate that to argue why the two paths must be path homotopic. And so let H be a path homotopy so let H be a path homotopy, between F tilde and G tilde. Now you can do that precisely. Look, it's precisely because of this assumption. You're assuming they have the same terminal point. You already know that they have the same initial point. You already know that, right? You already know this. So it's all about that terminal point. So since they have the same terminal point and they have the same initial point, F tilde and G tilde are path homotopic. So there's a homotopy between them. Now, I'm not calling it H tilde because I'm not lifting any H yet. I mean, it doesn't. You can call it whatever you want. I mean, usually the way we write H tilde is we start with an H and then we lift it. But here we're not lifting the homotopy. We're starting with the homotopy. So this is the homotopy between them in X, a path homotopy between them in X. And then, well, you project. Then by projecting, if you do pi composed H is a path homotopy between pi of F tilde and pi of G tilde. This is, of course, F, and this is, of course, G, because those are the liftings of F and G. So you have just constructed a path homotopy. If that's not clear, maybe this picture will help. This is our square. This is our square. Let me take this away. The square is being mapped into the covering space. And the covering space is being mapped by pi. So this is H. And the covering space is being mapped by pi into the base space. So if you compose, you see, it goes a little bit differently because in all of the other versions, we're constructing this map. But now the map is given to us, and we can just get a map automatically by just composing. So this is sort of the easy direction. So this would be pi composed H. And that now gives you a map from the square into Y. So this is a homotopy, right? It's a map of a square into Y between these two. So you've constructed a homotopy between those two. So that proves the other direction. So this is the monodromy theorem. And with the monodromy theorem, we can now prove something that's a little bit funny, but we've technically never proved this yet, is that we can use the monodromy theorem. We can use monodromy to prove that the circle S1 is not simply connected. I mean, the circle, if you have it has a hole in the middle, so of course it cannot be simply connected. So I'm not saying like this is some deeply surprising result in topology. Of course it's true. It's just nice to see how you convert that very simple intuitive statement into something that's very rigorous, and you can clearly show that in a very proper way. And once you have the tools to convert your intuition into something rigorous, then you can use those tools to start proving things that you will not be able to get with your intuition. So this is something we've stated before. In fact, we will prove more. So this statement is a much weaker statement that the fundamental group of the circle is isomorphic to the integers. This is, of course, saying a lot more. It's saying that not only is the fundamental group not trivial, it's actually isomorphic to the integers. So this is a weaker statement, but we'll see very soon how you get the fundamental group of the circle. I think for now, I just wanted to show you how you can use the monodromy theorem to justify this. Of course, we can do a lot better, but let's just show an illustration of this. So here's how you show it. So what you do is you consider is not, so we want to show the circle is not simply connected. So we're going to consider the exponential map, let's call it pi, from the real line to the circle. And the exponential map is given that pi of x is equal to e to the 2 pi I x. So this is the exponential map. And let's specify some initial conditions. So let's say we use the following initial condition. So this is 0 and this is 1. So these are convenient to use. Now, if S1 was simply connected, then every loop at the number 1, so let's call this loop F, would be path homotopic to the constant loop. So I think our notation for the constant loop is the letter E. And then you specify where the loop is constant. So it's constant at the number 1. So that's just the definition of what it means to be simply connected. If it's simply connected, then every loop, so let's pick a base point 1. So in every loop at that base point would shrink to the constant loop E1. So just to make sure what we mean, so E1 is the loop in the circle that's defined by the mapping property that for all time it's always equal to the number 1. Now, let F tilde and E1 tilde be the unique liftings of F and E1 into the covering space R, with the initial condition that F tilde of 0 is 0 and E tilde of 1 of 0 is 0. Right, so this is the initial condition that you've chosen. So then you have a unique lift. Now, so it's pretty straightforward to see. So observe that the unique lifting of the constant path is the constant path, but this is the constant path 0. If you're confused by that, it's because if it's being lifted, then you're saying that E1 should be equal to pi composed with E1 lifted, E1 tilde. But in the notation, in the exponential notation, you're saying that E1 should be equal to E to the 2 pi I E1 tilde. That's quite a lot of E's. That's funny, right? 2 different E's. But we're mature enough to tell them apart. Now, look at this. E1 tilde is always equal to 0. I'm sorry, E1, that's the constant path. It's always equal to the number 1. So then what should this exponent be? The exponent should be 0, right? It always stays 0. That's the unique way to do it. Because it has to start at 0, and then the whole thing has to remain 0. So this is the unique lifting. So the unique lifting itself is a constant path. So hence, by the monodromy theorem, if you look at the terminal point of f, that should be equal to the terminal point of the constant path. But the terminal point of the constant map is 0. Okay, so to summarize, if S1 was simply connected, then for any loop f at 1, so that's where it's located at, we would have that if you lift it to the covering space, then its terminal point will have to be equal to 0. And now you just have to come up with an example of when this does not happen. Then this is the example from before. So consider the loop f that's given by e to the 2 pi I t. Then the cover, like the lifting of the path, this is what we saw. This is basically the exact same example from before, but before we had the punctured plane. Then the lifted path is the path 2 pi I. This is, no, sorry about that. This is just t. Sorry, this is just t. Yeah, that's just t. Because since pi of f tilde of t is equal to, how is the mapping pi defined? This is e to the 2 pi I, and then it's f tilde of t. So therefore this has to be t to match with that. So it has to just be t. But then f tilde of 1, its terminal point is 1, not equal to 0. And that's the reason why the circle is not simply connected. This is not really, I'm not saying that this is the most elegant way to show that the circle is not simply connected. I think it's a lot nicer to just compute the fundamental group of the circle, like immediately. But I just wanted to illustrate, because we are talking about paths and lifting them and terminal points that are determined from the initial conditions. I'm only doing this because it just fits with the theme of the class. Like, I'm not saying that this is the way we find the fundamental group of the circle. It's just, I think it's just nicely fits with what we're talking about. And I want to finish, so now I want to finish with one last topic, and that is basically this. So say that x and y are two topological spaces, and f is a mapping between them. Let's write it like this. Is a continuous map. Then f induces a homomorphism between their fundamental groups. So you're going to have an induced homomorphism. Now, what does the word induced mean in mathematics? So if you've never seen this before, the word induced means you use one type of structure to create a new type of structure. So the example that I always like to give is that, say A is a matrix. So A is a matrix that has n rows and m columns. So then A induces a linear map. A matrix can always be used to create a linear map. And you can call the linear map, so the notation we often use in math is we take that object that is being used to induce something new, and you put a decoration on it. So we often use like a star, lowercase star or an uppercase star. So the linear map will induce, I'm sorry, the matrix can be used to create a linear map from Rm into Rn, where it's just matrix multiplication. So A star applied to an m-dimensional vector is the product between the matrix and that vector. So you will notice that we have an A here, we have the A here. This A is just the matrix, and A star is a linear map. It's no longer a matrix, but you're using a matrix to create a linear map. So that's like very common what one does in mathematics. Like you have one type of object, and then you're using that object to create a new type of object. So anyway, here, F is a map between topological spaces. The fundamental group is a group. So you can use the F to create a homomorphism between their fundamental groups. So then F induces a homomorphism between the fundamental group of X at X0 with the fundamental group of Y at Y0 as follows. So we have to say how this homomorphism is being constructed. So let's just recall what the fundamental group is. So this is, if you write it out in words, these are homotopy classes of loops at X0. So that's what it is. It's, you look at all loops in X. So maybe I should say in X. So these are homotopy classes of loops in X. Okay? So closed loops begin and end at X0. The loops are living in their loops, their paths in X. And then you identify two loops as being the same if there's a homotopy, a path homotopy between them. And this is the same, it's almost the same thing. This is homotopy classes of loops at Y0 in Y. So you want to define a mapping between them. So in order to define a mapping, you have to pick something in the domain and explain how to map it into the codomain. Okay, so now so we have to pick a closed loop. We usually use the letter F for a loop, but maybe we use a different letter this time because we're using F for something else. So how about we use the letter theta? I like to use the letter theta because it goes in a nice circle, so it looks like a loop. So let theta, and this is going to be something in pi 1 of x comma x0, be a loop in X at X0. Now I am being a little bit sloppy over here because it's not really a single loop. It's really an entire class of loops, and theta is just one representative in that entire class. So technically theta is the loop, but I'm being a little bit sloppy in the notation. So how can you create a loop in Y? Well, it's quite, if you think about it in terms of pictures, it should be quite clear. This is X, this is Y, this is X0, this is Y0. You have a loop theta in X. How can you get a loop in Y? Well, you have a map between them, so you just apply the mapping to theta and you get a loop over here. You just apply F. You apply F over to this one and you get something over here. So you're going to end up with something, it might go like this, perhaps. So there's going to be F composed theta. Okay, so if it makes it a little bit easier, do not forget that theta is a mapping from 0, 1 into X that begins and ends at X0. So then, if you do theta and you compose that with F, you will then have a map from 0, 1 into Y with F composed theta at 0 being Y0 and F composed theta at 1 also being Y0. So you're getting another closed loop. So here's therefore the way you construct it. So we construct F star as follows. So F star has to be a mapping from the fundamental group of X at X0 to the fundamental group of Y at Y0. And you're going to pick a class. So you're going to pick a homotopy class in here. And then we define, so this is how this map is defined, F star. It's going to take that class and it's going to map it to F compose theta. And now this is a homotopy class in the other one. So there's a number of things that you need to check. And they're not difficult, but they're kind of boring. You have to go through it. So you need to check that F star is well defined. That you see you're choosing a representative for the class. What if you use a different representative? Well, you might get a different loop, but it's going to be homotopic to the other one, so it's well defined. The second one, that F star is a homomorphism. It's a group homomorphism. So these things have to be checked. They're not particularly too difficult, but they're important. I mean, this is how you learn. So it would be better if you figure it out yourself how to do it. So this is called the induced map on the fundamental group. Now, I want to show you my favorite example of an induced map because it can lead to a lot of confusion. So this is a nice example. Let X be the circle. And let's say the point that we pick on the circle is 1. And Y would be the complex plane. And the point that we pick on the complex plane is also 1. Okay? And let F be the map from the circle into the complex plane, be the inclusion map. The inclusion map. So that just means that F of a point on a circle, so if you think of a point on the circle as a complex number, it's just being mapped to itself. So this is clearly a continuous map. So then, now notice, so note, F star is, I'm sorry, not F star, F is an injection. This is clearly an injection. An inclusion map is an injection. So this is an injective mapping. Now let's look at what happens with the fundamental group. So this map induces, that's our terminology, it induces, so we call this F star. It will now induce a map from the fundamental group of the circle F1 into the fundamental group of the complex plane F1. And how is this map defined? Well, here's the way it works. If you choose a homotopy class, theta, where does that homotopy class go to? Well, you compose it, and then you look at that class. But what is the mapping F? The mapping F is the inclusion mapping, so it's just itself. So you can just replace this. I mean, there's no need to write this. You can just write theta. So theta is being mapped to theta. It appears, so the notation is deceptive, it appears that F star, the induced map, is an injection or some kind of inclusion, right? The same thing is being mapped to the same thing. But if you think about it carefully, that's impossible because the fundamental group of the circle, even though we did not prove it, we all know what it is. It's isomorphic to the integers. And the fundamental group of the entire plane, not the, this is the entire plane, not the punctured plane. It's convex, so it's contractible. So in particular, its fundamental group is trivial. So this map will therefore induce. So you have this kind of situation. So you're mapping the integers into 0. So everything is being mapped to 0. There's no way this can be an injection. This is as far away from an injection you can be because everything gets mapped to the same point. So how does that make sense? So it's very deceptive notation. You see these square brackets over here. This represents the homotopy class in the circle. That's the homotopy class in the circle. These square brackets, this is the homotopy class in the complex plane. And the reason why this is not an injection is because you can take something that is not trivial homotopy-wise in the circle, but when you look at it homotopy-wise in the complex plane, it does become trivial. So namely the circle itself. So this is the circle. If you just choose the loop from before that goes around like this one time, this is theta, then theta is not homotopic, then theta does not shrink to a point within the circle, because within the circle there's no extra space to shrink it down to a point. So the homotopy class in the circle is not trivial. However, when you look at it, when you allow the extra space around it, right, you kind of put all of this in. Now when you look at theta as a homotopy class in the entire complex plane, then now you have all that space to shrink it down to a point. So it's just deceptive notation because it looks like theta is being mapped to theta. So it looks like it's an injection, but really you have to understand that these brackets have different meanings. This represents homotopy class in the circle. This represents homotopy class in the complex plane. So that's sort of the explanation. So what I like about this example is it's very deceptive. It's very simple. It shows you how it works out. And it also shows you this phenomenon that just because a mapping between topological spaces is injective does not mean that the induced mapping between the fundamental groups is injective. And it's also true the other way around. You can have a function that is not a surjection between two spaces. The induced map does not need to be a surjection between two spaces. But now I want to show you something interesting that happens with covering maps, So with covering maps. So with covering maps, the induced homomorphism on fundamental groups has a special property, a type of property that does not exist in general. But for covering maps, you have this property. So here's what I want to write over here. So this, let's write this as a proposition. And this will look funny. We'll have two different pi's. Let pi from x comma x0 to y comma y0 be a covering map. This is different from what we said before. Previously, we're talking about any continuous map, but now we're specifically assuming that we have a covering map. So then, the induced map from fundamental groups between the covering space to the fundamental group of the base space is injective. So that's the interesting property that it has. It is injective. Now, the original one, a covering map, is always surjective. That's the definition of a covering map. It is always surjective. So this is kind of funny. You started with something that's surjective, and when you take the induced homomorphism on fundamental groups, you now get something that's injective. Kind of flips the other way around. But this is only special, right? This flipping, so as a warning, so of course I should just add this warning. This flipping from surjective to injective is just a special phenomenon. This is not something that normally happens. It's because we have a very special type of continuous map, namely a covering map. So in particular, we say that the fundamental group of x at x0 is a subgroup of the fundamental group of the base space. Technically, it's not a subgroup because this consists of homotopy classes in X, this consists of homotopy classes in Y. But when we mean that something is a subgroup, we technically mean that you can embed it into this one. It's sort of like the way we write the integers is a subset or a subgroup of the rational numbers. I mean, the definition, if you look at the way you define the rational numbers rigorously, they technically do not contain integers, rather that the integers embed. There's like a very obvious way to embed it. The rational numbers, it consists of pairs of integers, right? Numerator and denominator. These are just integers. So, and in the same way, we say Q sits inside R, but if you look at like Dedekind cut definition of R, that's not really, Q is not really a subset. But I mean that this is typically what we mean. There's an injection, and this is the injection that sends that one to that one. So we say that the fundamental group of the covering space is a subgroup of the fundamental group of the base space. And how do you prove it? Well, this is the monodromy theorem, basically. Well, um, well, this is, well, this is just a, I mean, all it is, proof. So all this is the homotopy lifting property in disguise. That's all it is, because like, I think in the Braden book, he just says like one sentence or something. I'm not even sure he writes a proof. It just follows from everything. What, like, how do you show, like, how do you show that something is injective? If you have two things and they map to the same thing, then it means that the two things had to be the same to start with. That's what injective means. Now, think about this. If you have two homotopy classes and they map to the same class, then what are you saying? You're saying that the two loops, when you project them into Y, into the base space, they are the same. The same means there's a homotopy between them. But that homotopy, if you have a homotopy between them, that homotopy will then lift into a homotopy between them in the covering space. So that means they have to be the same in the beginning. So, so this is what I wanted to finish with, basically, that the covering map induces an injection on fundamental groups.